Hi, this is Mrs. Lemke, and again, Mr. Cubby and I tried again to record together, and super duper sad, it didn't work out. Bad quality sound. Ugh, sad. So I guess the one that you don't get to hear was our trial run, and this will be the one that you hear. All right, so picking up from where Mr. Cubby left off, another thing that is in the units 4 and 5 as the College Board defines them is the idea of L'Hopital's rule. And you can see that if you just, go on the internet and find a nice turquoise box about L'Hopital's rule, they write this lovely thing about 0 over 0 and some kind of infinity over some kind of infinity as being the two cases. Bear in mind that we need to be very rigorous here. We want to write the limit of the numerator as we do whatever it says equals something like 0 or an infinity. And we want to write the limit of the denominator is something like 0 or plus or minus infinity. And then we want to say that means I have an indeterminate form, which means I can apply L'Hopital's rule. So given that our test is not even a little bit multiple choice, it's all free response questions, this is the kind of thing I can see College Board being, ooh, yes, let's make sure they can write out L'Hopital's rule, because if they do some kind of like attempted cheating, they're going to find things like this and this. And we know that we as the College Board would like them to write this, the 3 bullet points. So just have kind of a little gut level feeling that that might be a thing. So remember that you're going to write all that out with appropriate mathematical rigor, that I have a top that is 0, a bottom that is 0, therefore L'Hopital's rule applies, or whatever the case may be, okay? Now L'Hopital's rule actually says that if I'm finding a limit of this and I have one of these forms, then that limit will equal the limit of the derivative of the top over the derivative of the bottom. Okay, so the first question on this slide is a classic. You probably just memorized this in math analysis, or maybe had some sort of graphical argument about how the sine curve and y equals x are really similar functions in the neighborhood of the origin. And therefore, I hope you know the answer to this one already. But even if you did not, you could now say, all right, well, the limit of the top as x approaches 0 is 0, and the limit of the bottom as x approaches 0 is also 0. So therefore, L'Hopital's rule applies to this limit. And then we could actually apply L'Hopital's rule, which says that the limit that I was given in the question has to have the same value as a limit of, and I take the derivative of the top and the derivative of the bottom. And then that is a limit that I can do with direct substitution, because cosine at 0 is 1. So that answer is 1. All right, over here, this is the more complicated kind of L'Hopital's rule, because if I were to say substitute in, quote unquote, an infinity, oh my gosh, that kind of gives me the heebie-jeebies to say, but this is in the form of something that's going toward infinity raised to a power that is approaching 0. So it's an infinity to the 0 kind of form, which is indeterminate, but it's not one of the good kinds. So I'm going to have to manipulate this to get a 0 over 0 or an infinity type over infinity, that kind of thing. Okay, something that was on that previous slide. So here I'm going to define a new variable. I'm going to let y equal that expression. And then I'm going to take the natural log of both sides, because that allows me to use the lovely properties of natural log. And then I'm going to rewrite this as a quotient. That says natural log, not limit. My handwriting is the worst. Okay, so we've got this. All right, so now I'm going to slide back into limit life. And so limit as x approaches infinity is what I was considering. So apply that limit statement to both sides of this expression. And now I can say, do I have the good kind? Do I have a L'Hopital situation? Well, sorry. So the limit of the numerator as x approaches infinity is approaching infinity. The limit of the denominator as x approaches infinity clearly is approaching infinity. And so therefore L'Hopital's rule applies. Write the thing, blah, 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 blah. Okay, so you write that, and now we can utilize L'Hopital's rule. So my limit of natural log of x over x is going to be the same value, is going to have the same value as a limit of the derivative of the top over the derivative of the bottom. And as x goes to infinity, this expression is going to approach 0. But I need to bear in mind that this expression was equal to the limit of natural log of y. Y is the thing that I defined in the beginning of the question. And so if natural log of y approaches 0, right, read from there to there, then that means my limit of y has to be e to the 0, which is 1. So this question also has the answer of 1 when all is said and done. Right, that was L'Hopital's rule in a nutshell. Here's mean value theorem in a nutshell. So mean value theorem, you probably think of in kind of two different modalities. It's actually the same theorem, but when we're thinking about derivatives versus when we're thinking about integrals, our brains maybe work a little bit differently. The math itself is the same, which is why it has the same name. Now, usually when people just say mean value theorem, they're thinking of it the derivatives way. And if we're thinking of it the integrals way, we add on the words for integrals, okay? But just for clarity, but you could just say mean value theorem actually for both because it is the same. All right, so the mean value theorem for derivatives, so to speak, is the one that says that the average rate of change, which is just the slope of a secant line, is equal to the slope of some tangent line in between A and B. So there's a picture that would go with that. Let's see if I can draw. This is always a question. Can I draw? So if I had a function, and let's say that A was over here, and B was over here. And then the line that connects those, in other words, the secant line, would have some particular slope. And in the way that I drew this, it appears that there's actually two different places, okay? So this actually has maybe a little bit of a wording issue. There exists at least one, it should say, at least one number C, such that the slope at this location, slope at this location, are the same slopes as what you would get over the interval. So the tangent line slope somewhere has to equal the secant line slope over the interval. In other words, the instantaneous rate of change someplace matches the average rate of change over the interval. So the mean value theorem for integrals, you're thinking more in this situation about area. You say, all right, here's A, here's B. I've got some graph, blah, okay? And here is my interpretation of this side of the equation is to think about area under the curve. So here's my area. And that area has to be the same amount of space as what I would get taking the interval from B to A. So this width is B minus A in terms of a length. And then there's some place, let me kind of judge where this is, maybe here-ish. There's some location C, really didn't think that through, that's C. Okay, so there's some x value C at which the function value at C makes some height, and then this box, this rectangle, has the same area as the yellow part. So it's like this little yellow space that's left over up on top that kind of like slides in here is the idea, okay? So the area of the rectangle, the special rectangle, the area of that special rectangle is the same as the area under the curve. Now, I think it's easier to see that these are the same theorem if we manipulate a little bit. So on the left side of this slide, you see the average rate of change equals the instantaneous rate of change at some location C. If you reorganize the mean value theorem for integrals, quote unquote, then you have f of C equals the integral divided by the interval. Integral interval, that's weird to say. Okay, so Mr. Covey pointed out to me in the recording that you are not hearing, sad, that these two are the same because you say something like on the one over here, you could say the average rate of, or the instantaneous rate of change equals your average rate of change. And over here, this is like your average value of your function, right? Your average value at a location C, that's how you find average value right there, it defines it. So you can kind of see that these are similar. I even like to take that integral step because I sometimes look at that and say like, what is that even? Use your fundamental theorem. And I think you can definitely see that these are the same thing at this juncture, right? Look at the two that I just circled. Those are the same statements. It's just a matter of what layer you're on, right? So here, if I take the antiderivative of f prime, I get f. Here, if I take the antiderivative of f, I get capital F. It's the same theorem, okay? So just wanted you to realize that. Even though one we kind of think about slope and the other one we think about area, the math is the same math. All right, this is one of my favorite handouts in general, like when I teach a class where you start from the beginning of calculus, when I used to teach AB or when we used to have our CP calculus class. This handout basically tells you chapter 3 in our textbook in one piece of paper. So I don't really think I need to talk about this piece of paper per se, or this slide, but I am going to give you just a few minutes, like you can hit pause at some moment and just read through these 4 like columns of bubbles or reasoning and just verify that you do in fact know how to find extrema using the first derivative test, using the second derivative test, that you know what concavity is, you know how to find a point of inflection, all that, okay? I do believe you know this. I don't believe you need me to say it. I'm rambling right now to give you a second to find the pause, if you need to pause. Okay, I think you're back. And the last thing that is mentioned in the College Board CED Units 4 and 5 is optimization. Now, honestly, optimization, you guys, it's just max-min problems. In fact, back in the day, before the graphing calculator, late 80s, early 90s, when I was taking calculus classes, we would call these applied max-min problems. So when I started teaching calculus, I'm like, optimization, what is that? And then I realized it just had changed names. So it's just a max-min problem where there's a story. That's it. Now, at the time that you did these in math analysis, they were maybe one of the harder things that you had done, but you've done so much more math since then that I bet you look back at this and I'm like, what was my big problem with this? It's not that bad. Okay, now given the way that our test is formatted this year, I think it's really unlikely that you see this on your exam. That said, it's still good to know, all right? So, and I also can be wrong. So this is a funny little question. I'm going to read it to you, and then I'd like you to pause the video and try it, okay? And then come back and see if you got it right. So suppose you have invented a new and delicious beverage called Schwab, and it's Schwab with an exclamation point or possibly a factorial, which tastes inexplicably like cotton balls. It's kind of a bad invention, unless the cotton ball taste makes people want to drink more because they're thirsty. Then it's genius. Deemed to be the least refreshing drink in the known universe, it is nonetheless flying off the shelves. If you wish each cylindrical can of Schwab to contain 100 cubic inches of beverage, then what height should you make each can to minimize the amount of aluminum you use to manufacture the can? So you want to minimize your surface area. You're looking for that magical height. They gave you a constraint of the volume, okay? Please pause the video, draw out a picture, see if you can figure this guy out. Okay, I'm just going to flip through the solution with you. I hope that you tried that yourself. Okay, so remember that a cylinder is comprised of 2 circles, the top and the bottom. as well as the rectangle. That rectangle goes around the can. And you can see that the top edge of the rectangle, as it's drawn here, is 2 pi r because that's the circumference of the circle. It would have to go around the top of the can. Then they gave you, or you should be able to figure out that the surface area, therefore, would be 2 pi r squared, it's 2 circles, plus the area of this rectangle, which is the 2 dimensions multiplied together. So this is the rectangle, this is the top and the bottom, and so altogether that's surface area. They also told you that the volume of the can had to be 100. Now if you use this, you can get a statement for what the height is relative to the radius, and then substitute that back into your surface area equation. And the reason that you want that is because you need to have a function, like a function of area, that only depends on radius. Previously, you had a function of area that depended on radius and height. That's too many variables, okay? So we want an area function that only depends on radius. So get that, and then just like always, if I'm trying to find an extrema, I'm going to take a derivative, I'm going to find critical numbers, I'm going to do some kind of testing. And so that testing leads me to the fact that my critical number is when r equals that. And so plug that in and find out when h, what value of h there is, because that's what they asked for. The question did not ask for r, it asked for h. And so make sure you substitute it back in. Because I had a negative derivative value that went to a positive, negative to positive means I have a minimum. So that is the right kind of extrema. All right. That's all we had for you today. I'm sorry that the video was in 2 pieces. It is tremendously sad. So you will definitely be sent or be getting, I'm not really sure exactly how we're going to do this yet, but it will be clear. You are going to receive a free response question to work on that we want you to finish by Wednesday at 4 o'clock. And you also will get some information about doing some more of the personal progress checks on AP Classroom. Thank you so much, you guys. Hang in there, get outside, and be well.